say that again. The only difference here is the change of what the statistic for the standard deviation. Okay, so instead of what sigma, we have S, which is the sample standard deviation. Good. Then when the sample size is small, you are also going to use the T statistic. Okay, the T statistic has the same formula. It's X bar minus mu over S divided by what? Square root of N. So one will ask, what is the difference between the two then? Okay, the difference between the two is, you see, when we are formulating the critical values, you go and read your Z value from the Z table, which is the standard normal table. But you read the T value from the student T distribution table. You go and read the T value from what? The student T distribution table, okay, like this for a one-tail test. And we'll see how to do that subsequently in an example. So let me summarize. The key point here is, once your variance, population variance is not given, or the population standard deviation is not given, you first have to consider, is the sample size large or small? If it is large, then we'll still use a Z. If it is small, we'll use a T. Okay, they have the same formulas, but the Z will be read from the standard normal table, and the T will be read from the student T distribution table. Good. Let's proceed. So I think I've touched on this last week, having a left rejection and right rejection and true tail, which is good. So let's revisit the example we did last week. We will not be solving it though, but we just want to touch on the key, the test statistic point, which is the 0.3, which we are discussing in class today. Okay. Sorry. So when we look at this, it says a random sample of 1,000 iron rods. Okay, N is 1,000 with an average length of 71.8. So X bar is 71.8. Assuming the population what? Standard deviation. So you can see that the population standard deviation, sigma, has been given. So it is known. So the moment sigma is given, you don't even ask of the sample size. You go straight away and use sets statistic. That's what I'm saying. So once it is approximately normal and sigma has been given, you make use of what? The set statistic. Okay. Good. Because sigma has been given. Right. Good. We've solved this one in class, but we just want to touch on the selection of the test statistic. And that is why we are revisiting the same example. Now let's go to another example to see a difference or the variation. Okay, there. So let's take this example too. So in this example, it says MTN company claims, this is a claim, that the average length of all the phone calls they do on their network, okay, is 8 minutes. So average is equals to what? 8 minutes. Okay. And then the opposite statement will be average is not equal to what? 8 minutes. You understand? Good. Now, he says a random, so he says in a random sample of what? N equals to what? 58 phone calls. So our sample size is 58. 58, right? And then it says the sample mean was 7.8. So X bar is what? 7.8. And the standard deviation, remember, the standard deviation here is on the random sample. They didn't say the population standard deviation. So the standard deviation for the sample, which is standard deviation S, is 0.5. Okay, good. Is there enough evidence to support the claim? So once again, I'm going to touch on the step 3. We'll solve the whole question, but let's touch on the step 3 first. So we said in selecting our test statistic, you first check whether sigma has been given. So in this question, sigma is not given, and there is no sigma. Sigma or sigma square has not been provided. It's rather the sample standard deviation that was provided. So what's next? You have to now ask yourself whether your n is greater than or equal to 30, whether it is large. Okay, if it is large, then you still use the Z statistic and replace what sigma with S. But if it is small, then use the T statistic. That is what we said. So clearly here our n was what 58, which exceeds 30. Okay, it exceeds 30. So we are going to make use of the Z statistic here. So you can see the Z statistic is being employed, okay, in the computation over here. Now let's go down to the details and solve the entire problem. So I'll go to the whiteboard and solve that. Let's solve it together. Good. Yeah, so let's write our parameters. We had our H naught, which was, we said average length of phone calls was equal to 8 minutes. Then not equal to will be the alternate hypothesis, which will be HA. So that is step 1, right? Step 1. In exams, I will be expecting you to write them in steps for me. Okay, I don't want you to pretend as if you are experts. So step 1. Step 2. Step 2 is to state your significance level. So alpha here is 0.05, 0.05, which is 5%. Okay, then let's write the given parameters, which is n was 58. I think x bar was 7.8. And our S is 0.5. 0.5. Okay. So we step 3. Yeah, so we said because sigma was not known, since we provided a sample standard deviation, but our sample size is larger than 30, we use a statistic, which is what? Which is x bar minus mu over S divided by the square root of what? 58. Sorry. Since we are quoting formula, let's keep everything in the formula form. So this will be 7.8. Okay. Minus what? Minus 8 over standard deviation is what? 0.5 over the square root of what? Square root of 58. Good. So once we do the calculation, okay, over there we have so we have negative 3.05 minus 3.05, okay, for the calculated value of the Z. Then step 4 is to formulate our decision rule. Okay, so we'll go back, draw the curve. You always have to draw the curve, okay? So we draw the curve and indicate the rejection region. So our center is always 0. And yeah, to indicate the rejection rate, like we said, look at the sign on the alternate hypothesis. Here it is not equal to. Not equal to means it is either less than or greater than, right? So which means it's two-tail, two-way rejection. And we said for two-way rejection, you divide the alpha into 2, okay? So we are going to have this side being alpha on 2, alpha over 2, which is 0.05. Sorry, 0.025. And then the other rejection on the right side also what? 0.025. 0.025. Okay. So we got this and we got this here. Good. So we are going to read a critical value, which is Z with that probability of 0.025. Okay, and it will be the same value on the right side. So we need not bother ourselves since the graph is symmetric. Let's just find the value on the left critical value and negate it to get the right side. Okay, which will take us to our standard normal table. We have to go to the table and find the probability of 0.025. So I'm going to first, yes, let me attempt opening my table from here. It will take a while, but we have to. Okay. Yeah, so that's the standard normal table. Good. And we are looking for 0.025. Okay, that's 0.025. That is the probability we're looking for. So let's go down, down, down. There's 0.0. No, there's 0.00. This is 0.01. So we are getting close. 0.02. 0.022. Okay, so let's go down. 0.03, 0.04. Sorry, 0.024, 0.025. So this is the value we're looking for. Okay, so let's draw a straight line, horizontal line, and then a vertical line which intersected to give us that probability. Okay, so once we got this, we can read the Z value, which is minus 1.9, okay, with the second decimal place, which is what? Which is 6, okay? So our critical value is negative 1.96, okay? Very well. So let's go back to our whiteboard. Okay, so which means that we have our lower threshold values as minus 1.996 and then 1.96 here, 1.96. Okay, good. Then the question is, what next? Once you formulated your critical values, like we said, they are your minimum and your maximum value when you are going to the market. Okay, so beyond these prices, you eventually, in fact, you end up rejecting, okay, whatever claim somebody out there is going to make for the price of a product. So we will compare the calculated value, which was based on the sample data, okay, which we picked, and that is negative 3.05, okay. And clearly, when we talk about negative 3.05, that is way on the left, way below your minimum critical value here. Okay, it's way below that value. So if you plot it, it's going to lie somewhere here, which means it's in the rejection. It's within your rejection region. Okay, it's within your rejection region. So when that happens, what do? We say that at a 5% or significance level, we have enough evidence to reject the null claim. Okay, good. Then you make evidence. Your conclusion. Once you have rejected the null claim, meaning that you are rejecting this claim, then it means that mu, which is the average length of phone calls, is not equal to 8 minutes. Okay, it's not equal to 8 minutes, which means a claim by the MTN company, okay, is not valid. Good. Yeah, so we'll go back to our original screen. If you have any questions, you can ask. If there are any questions, you may ask. Yeah, Richmond.
Sir, please, can you go over what you just said again, please?
Okay, so Richmond is clear. You are not really focusing. Your environment is very noisy. But how about I'll just touch on the very final point. So we said once you compare, you see from the diagram here, let me magnify that a bit for you. Okay. Once you compare the value, once you compare the calculated value with your critical values, and you plot it on the graph, you find out that it's in the rejection region. So if it's in the rejection region, you reject. It's like you went to buy a phone and you know the price of the phone is from 500 to 1,000 cedis. And then you get there and the person says that my phones are so cheap, so I'm giving it to you for 50 cedi. You know it's either a stolen phone or a fake phone. You understand? So you reject it. The same way when you get there and they tell you that this same phone is for like 5,000, you know that is not true. So you reject it. So either way, when you are below your minimum threshold or above your maximum threshold, you have evidence to reject the claim, which is the null hypothesis. Okay, cool. So that is what we were saying, that at a 5% level of significance, okay, there is enough evidence to reject the null hypothesis, or the null claim, that the average length of the phone calls is 8 minutes. And then you conclude on the fact that then it means that the average length of phone calls exceeds is not equal to 8 minutes. Okay, so let's continue since there are no other hands up. We want to look at the next example. So over here we have a different scenario, which is the case 2 for sigma not known and small sample size. Okay, so here it says a local telephone company claims that the average length of phone calls is 8 minutes. In a random sample of 18 phone calls, the sample mean was 7.8, same parameters, okay? Just that this time around, our sample size is 18. 18, which is less than 30. Good. And again, the standard deviation here is for the sample. So sigma is not given. It's not given. We only have the sample standard deviation. And the sample size is also less than 30. So which means we are going to make use of the T statistic. Okay. So you still go through the same process. Step 1, which is state your claim. Step 2, which is alpha. Then step 3 will be T, which is the same formula. Okay, so once we calculate it, here we have negative 1.6769697. Okay, good. Then what's next? We have to determine our critical values. So to do that, let's go to the board. N is 18. Okay. Okay. Yeah, so this time around, like I said, the difference between the Z statistic and the T statistics lies in the reading of the table. Okay. And this time around, we are going to make use of the T distribution table, not the standard normal table. And once again, the sign on the alternate hypothesis is mu is not equal to 8, okay, 8 minutes. So which means we have a two-tailed test here. Okay. And what we are here to read is T with alpha on 2 and then n-1 degrees of freedom, which is negative, and the positive side will be T alpha on 2 n-1 degrees of freedom. Okay, so the question is, how do we read this? Okay, and this simply means that we are going to read T with alpha on 2, we all know is 0.025. Okay, and then your n was 18, so 18 minus 1 will give us 17. Okay, and once again the graph is symmetric, so you just read the left value and then you negate it. Okay, so we want to read a T table. Let's go back to the slide and read the T table. Good. Good. So this is the T table. On the T table, this is the degree of freedom, the DF. So the DF, which is your n-1, okay, right, is what you have here. We write it as, okay, chi over here, which is degrees of freedom. And then your alpha is what you have up here, okay? So these are the alpha values. And we said we were reading T with alpha of 0.025. This is it. And degrees of freedom 17. So this is it. So we only have to draw a horizontal line and a vertical line and check the point they intersect. And this is the critical value. Okay, good, which is 2.110. 2.110. Now let's go back to our screen. Okay, fine. Let's just go here. There's no need to go back to the board. So this gives us the margin. So this gives us the critical value. This is your minimum value, which is minus 2.110, and the maximum value is 2.110. So which means any value you calculated here if it falls, okay, on the left of the minimum, you reject. If it falls on the right of the maximum, you reject. Okay, but if not, and it falls in between the two, this is an acceptance region. Okay, an acceptance region here. So let's see where negative 1.69 falls. Negative 1.69 is between 0 and the lower. It will lie somewhere here, half of whatever we have. So it means that that value which we calculated lies in the acceptable region. It's in the acceptable region. So if it is in the acceptable region, then we say by reason of our inference that we're at 5% significance level, we do not have evidence, okay? We do not have evidence to reject the null hypothesis, okay? So we do not have enough evidence to reject the null hypothesis. If that is the case, then we conclude that the average length of phone calls is 8 minutes as claimed by the company. Good. So that is how you go about with the T statistic as well. If there's any question, I think I saw a hand along the line. You can raise your hand and ask your question. Yes, Joseph. Joseph.
Yeah, yes, sir. Good evening, sir.
Yeah, evening. Go straight to your point.
To be frank, your voice was too down, so I couldn't hear anything, please.
Okay. The video will be posted, you hear it. Okay. Any questions so far? Yeah, Bernard. Bernard. Godfred.
Yes, sir.
Yes.
Good evening, sir.
Good evening.
Yeah, so mine is about the video you just mentioned about I'm following, but then anytime I try to, I hope when we are done, you get some time to really give us a specific, because anytime I enter the Micropobi, I get I get 1 or 2 videos, but some of them are even from last semester. I'm not able to get like, so I don't know how to get to you. So I hope by the end of the lecture, you might be able to tell us how to get practically maybe more than half of what you have put online so that we can know how to go on. Because mostly when I go there, all I get is the same thing. I don't get anything different.
Okay, so to respond to that, I always send you the link to the video, and they are on LMS as well. I send it. Bernard, go ahead with your submission. Okay, I guess his network is a bit poor, but you can still type it on the chat page. We'll look at it and respond appropriately. Okay. So the next thing we want to look at, okay, is to examine what we mean by confidence intervals. But before that, there is an assignment here which I expect you to do, okay, before you come to class next week. Now, in this example here, particularly for the second question, the first question is straightforward. But for the second question, you see here the data has been given. You were not given the sample mean, you were given the whole sample data. So you will have to find a sample mean, and you also have to find a sample standard deviation. Okay, and we all know how to find mean and standard deviation, but you have to use the sample standard deviation formula, okay, as I explained in class. So take note of that. So that is a clue to solving this problem. Now, I think there's a charge. I don't know, but from my end, specific. So anytime we create an interval so that we are expecting the value or the price of the item we are going to look for to fall within those two values, we are creating a confidence interval. Okay. So like I said, first you would have taken sample data, and then you know that the mean of, for example, a phone, the average price is 600. Then before you go to the market, you say, okay, well, let me budget for some plus or minus 100 cedis. So it's from 500 to 700. And within this interval, I should have my phone, okay, lying within this interval, okay? Good. That is what the whole concept of confidence interval is. That is generating an interval within which we expect that our true population being will lie within. Okay, how do we do that? It's by logic, what I just explained. So for example, if I ask you to create a CI or a 95% CI, okay, what now another thing we need to understand is if I say 95% CI, meaning we are 95% sure, okay, then it means that we are also 5% not sure, which means within 5%, we are not sure. We are likely to not have the population mean falling within that interval. That is rejection. Okay. So the alpha will be the rejection, which is 5%. Okay. So if CI is 95, then alpha will be 5%. If CI is 90, then alpha will be 10%. You understand? That is what this whole thing is. Good. So if I ask you to create a CI on, let's say, for example, the claim that was made by the MTN company, where N was equals to 58, where the sample size was large. So for 58, the sample, we also told that the sample mean was 7.8, right? From that example. So if you are creating a 95% confidence interval, it's just going to be your X bar, which is the observed mean or the sample mean, plus or minus what? Plus or minus our Z alpha on 2, okay, times what? Your standard deviation over the square root of N. Okay, I've seen a hand up. Anytime I come, the hands are gone. Okay, let's continue. So that should give us 7.8 plus or minus. Then the Z value we calculated, if you remember, when we read the Z table, we had 1.96 and negative 1.96, right? So we can put 1.96 there, which is Z alpha on 2. So 1.96. Okay, then our S was giving us 0.5, if you remember. So this is 0.5 over the square root of what? 58. Okay. So do this calculation for me. 1.96 times 0.5 divided by 50, the square root of 58. Calculate just this side for me. So when you do that, you put it on the chart for me. So thank you. We have the answer to be 7.8 plus and minus 0.128. Okay. So it's just a matter of subtracting this value and then adding this value. So it means we have the interval of 7.8 minus 0.128 should give us 7.6, okay, 672, 0.672. And then when we add to that, that should give us 928. So this gives us our upper margin and the lower margin within which we expect the population mean to lie in a 95% what confidence. Now, let me just touch on this. Just like when you were going to the market, okay, you decided to add 100 cedis and deduct 100 cedis from the expected value, which is the 600 cedis, okay? We call it the plus or minus, which is the margin of error. So when you go, you are giving yourself some allowance of error, so that when you get to the market and the person says, oh, it's not 600 cedis, so the price has been increased, it means you have catered for that. And when you go there and you're able to negotiate well, then you beat down the price a bit. Okay, so we call this quantity here, okay, the whole quantity which we are doing the plus or minus to the sample, the margin of error. Okay, so this is called the error margin or the margin of error. So you take note of that. So the margin of error is always the plus or minus on that sample mean. Good. Now, so somebody will ask, okay, sir, so what if our sample size was less than 30? Okay, then we follow the same procedure. The only difference is instead of Z, we're going to make use of a T. Okay, so in the second scenario where scenario, let's clean all of this, where our sample size was 18, okay? In the second scenario where our sample size was 18, if you recall, our critical value was 2.110. So the critical value was 2.110, okay? Good. So here too, we're reading T with alpha on 2, and then n minus 1 degree of freedom. Let me clean this. So alpha on 2, n minus 1 degrees of freedom. That is the formula. Okay, and when we read it, we had 2.11 times 0.5 over 18, because the sample size is 18. So you have to recalculate and give me the value for the margin of error. So calculate a section for the margin of error and give me the estimate. We have 0. So this gives us 0.248 or 25, if you like. 0.248 or 25. So we will just subtract from the sample mean and add to the sample mean. You get it? So when we do that from here, this should give us 0.5. Okay, 5.552. Okay, so 0.552 for the lower margin, and then for the upper margin, we expect what? 8 points. So that should be 8.048. Okay, so this gives us our lower and upper, okay, confidence intervals for the true population mean. Okay, and then once again, this is within a 95% CI. Okay, good. Then somebody will ask, say, what if the confidence interval changes, or if our alpha rejection region changes? Okay, rejection region changes. Now, let's try that example, then I'll come down to a little theory. Good. So, which means that in this case, let's say we want to develop a 90% confidence interval. If it's 90% confidence interval, then our alpha is 10%. Okay. So 10% means 0. What? 0.1. And since we are looking at a two-tail, two-tail confidence intervals are always two-tail. So we have what? Alpha on 2. So alpha on 2 will be 0. 0. What? 0.05. Okay. So when we are reading this value, so for example, when you are reading this one for a small sample size scenario, okay, you will be reading. Let me clean the thing. So let me clean this whole section. So this time you'll be reading T with 0.05, not 0.1. Oh, it is alpha, okay, divided by 2. So 0.05 and 17 degrees of freedom. That is in the case where our sample size is 18. Okay. Then you bring your sample, your standard deviation over the square root of n. So this is what you have to read from the statistical table. Okay. So let's do that immediately. So statistical table, we want T with degrees of freedom 0.05. Where is that value? Yes. So okay, let's scroll it down a bit to allow us to see. Yeah, so the value, the 0.05 value we are looking for. Okay, let's color it green. This is the 0.05. For those who cannot see, let me use black. This is the value we are talking about, 0.05. Okay, and the degree. So let's just rule the line down. And the degree of freedom, which we are looking for, is 17, right? So when we go down, 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 okay, that will be this value here, where the two of them intersects. 17 and this value will give us a T value of what? 1.740. Okay, 1.740. So let's go back to the example we're looking at. Good. Good. So, oh, sorry about that. I think the value was 1.747, that is 1.740. So let's go back and put it into the calculation. So we just come and write it here. That will be 1.74 times the standard deviation, which we know as what? 0.5 over square root of what? 18. Okay, good. So that will be the margin of error here. You understand? And always, this is always plus or minus. So we're going to calculate this session and then add it and subtract to give us a confidence interval. Good. In the same way, if it had been for n, which is 58, meaning that you'll be using the Z statistic. If Z statistics, then this one will be Z with, let me clean this side. So it will be Z with what? A probability of 0.05. Okay. Z with a probability of 0.05. So when you go to the Z table. Let's see if we can find that quickly. So you get to the Z table. Z table, because of the writings, it might be difficult for us to. Okay, but all the same, that is 0. We are looking for 0.05. So you go down a bit. So 0.05 will be down here, which is this value. I think we saw it earlier in class. This is the value, which is 1.64, okay, 5. But for now, let's just use 1.64, right? In class, 1.64. Good. So this is it. This is the 1.64 I'm talking about. So you rule this line and then you rule it up and you get your 1.64, okay? Let me clean this one. Good. So once you rule up, you get your 1.64, okay, as we have said. Good. So if that is the case, you just come back and then put it into your table here, okay? So in the case of that, of Z 0.05, this is what this is 1.64 times this. Then you compute the margin of error, add it and subtract to form your confidence interval. Good. So on that note, we'll come to a conclusion of my presentation. And I would like to take some questions from the class, if you have any.